Sound is something we experience constantly, but have you ever stopped to wonder what it really is and how it travels? The honk of a car horn, the chirping of birds, or the hum of a refrigerator, these everyday sounds reach our ears, yet the process that allows us to hear them is both fascinating and complex. The science of sound takes us into a world of vibrations, air molecules, and waves, all working together in an invisible dance that allows sounds to move from one place to another. Understanding how sound travels not only helps us appreciate the sounds we hear but also opens up a deeper knowledge of the physical world around us. At its most basic level, sound is a type of energy. This energy is produced when something vibrates. Picture a guitar string being plucked. As your fingers pull and release the string, it starts to vibrate rapidly back and forth. These vibrations disturb the air molecules around the string. As the string moves, it pushes nearby air molecules together and then pulls them apart, creating tiny pressure changes in the air. These fluctuations in air pressure are what we call sound waves. Now, imagine dropping a stone into a still pond. The stone hitting the water creates ripples that spread outward in all directions. Sound works in a very similar way, except instead of water, it's air molecules that carry the vibrations. When an object vibrates, it sets off a ripple of sound waves that move through the air. These waves spread out, transferring the energy of the original vibration across distances, eventually reaching our ears. But sound doesn't just travel through air, it can move through any medium that has molecules, like liquids and solids. This is because sound relies on the movement of molecules to carry its energy. If you've ever put your ear to a railroad track or pressed it against the wall to hear voices in the next room, you've experienced sound traveling through solids. In fact, sound can travel faster through solids than through air. This is because the molecules in a solid are packed more tightly together, making it easier for the energy of sound to pass from one molecule to the next. In the air, sound travels at a speed of about 343 meters per second, or roughly 767 miles per hour, under normal conditions. However, this speed isn't constant, it can change depending on factors like temperature, humidity, and altitude. In warmer air, sound travels faster because the air molecules have more energy and move more quickly, allowing the sound waves to pass through more efficiently. On the other hand, in colder air, the molecules move more slowly, and the speed of sound decreases. Sound traveling through water is an even faster phenomenon. In water, sound moves at about 1,500 meters per second, which is roughly 4 times faster than in air. This is because water molecules are closer together than air molecules, allowing sound waves to move more quickly. Dolphins and whales rely on this property of sound in water, using echolocation to navigate and communicate across great distances in the ocean. Their clicks and whistles bounce off objects and return to them as echoes, providing a sort of underwater map that helps them find food or avoid obstacles. Interestingly, sound can't travel in a vacuum, like the vacuum of space. This is because sound needs a medium, like air, water, or a solid, to carry its waves. In the absence of molecules to push and pull, there is no way for the vibrations to move from one place to another. This is why astronauts can't hear each other in space without the help of radios or other devices that convert sound into electromagnetic signals. So, how does sound travel to our ears, and how do we actually hear it? When sound waves reach our ears, they travel through the ear canal to the eardrum, which is a thin, sensitive membrane. The sound waves cause the eardrum to vibrate, just like the original object that created the sound. These vibrations are then passed along to 3 tiny bones in the middle ear, known as the hammer, anvil, and stirrup. These bones amplify the vibrations and send them to the cochlea, a spiral-shaped organ in the inner ear filled with fluid. Inside the cochlea are thousands of tiny hair cells that move in response to the vibrations. As they move, these hair cells convert the mechanical energy of the vibrations into electrical signals. These signals are then sent to the brain via the auditory nerve. Once they reach the brain, the signals are interpreted as sound, whether it's the melody of a song, the bark of a dog, or the laughter of a friend. The human ear is a remarkable organ, capable of detecting a wide range of sounds, from the faintest whisper to the loud roar of an airplane engine. But not all sounds are audible to us. The sounds we can hear fall within a specific range of frequencies, known as the audible range. This range typically spans from about 20 Hz to 20,000 Hz. A sound's frequency is the number of times the waves vibrate in 1 second, and it's measured in hertz. Low-frequency sounds, like the rumble of thunder, have longer wavelengths and vibrate more slowly, while high-frequency sounds, like a bird's chirp, have shorter wavelengths and vibrate more quickly. Some animals can hear sounds beyond the range of human hearing. For instance, dogs can detect frequencies up to about 65,000 Hz, which is why a dog whistle, which emits high-pitched sounds inaudible to humans, grabs a dog's attention. Similarly, bats use high-frequency sounds, known as ultrasonic waves, to navigate and find prey in the dark, a process called echolocation. While sound is a fascinating natural phenomenon, it's also shaped by our environment in intriguing ways. One important factor that affects how sound travels is reflection. When sound waves hit a surface, they can bounce back, creating an echo. This is why shouting into a canyon or large empty room produces an echo that repeats your voice. The smooth, hard surfaces reflect sound waves more effectively, while softer, more porous surfaces, like carpets or curtains, absorb sound and reduce echoes. This principle of reflection is harnessed in the design of concert halls and theaters, where architects carefully design the shape and materials of the walls and ceilings to enhance the acoustics. The goal is to create a space where sound waves reflect in such a way that every seat in the house receives clear, balanced sound. It's a delicate balance of reflection and absorption, as too much reflection can make the sound overwhelming, while too much absorption can make it feel dull and lifeless. Diffraction is another way sound interacts with its environment. Diffraction occurs when sound waves encounter an obstacle or pass through an opening. If the obstacle is smaller than the wavelength of the sound, the waves bend around it and continue on their path. This is why you can still hear someone speaking even if they're standing behind a wall or around a corner. The sound waves diffract, or bend, around the obstacle, allowing you to hear what's happening on the other side. Refraction, on the other hand, is the bending of sound waves as they pass from one medium to another or through layers of air with different temperatures. For example, if you've ever been to a lake on a cool morning, you might have noticed how sounds from across the water seem unusually clear and loud. This happens because the cooler air near the surface of the water bends the sound waves down toward the ground, making them travel farther than they normally would. In contrast, on a hot day, the opposite can happen, with sound waves bending upward and away from the listener, making distant sounds harder to hear. The study of sound, or acoustics, has led to numerous technological advances that affect our everyday lives. Microphones, speakers, and headphones are all based on the principles of sound waves and vibration. A microphone works by capturing sound waves and converting them into electrical signals, which can then be amplified or recorded. The diaphragm inside the microphone vibrates in response to the sound waves, similar to how our eardrums work. In reverse, a speaker takes electrical signals and converts them back into sound waves, vibrating a diaphragm to produce the sounds we hear. Sound has also found important applications in medicine. Ultrasound technology, for example, uses high-frequency sound waves to create images of the inside of the body. By sending sound waves into the body and measuring how they bounce back, doctors can get detailed views of organs, tissues, and even developing babies in the womb. This non-invasive technology is made possible by our understanding of how sound waves travel through different mediums. Another fascinating application of sound is sonar, which stands for sound navigation and ranging. Sonar is used by submarines and ships to detect objects underwater by sending out sound pulses and listening for their echoes. The time it takes for the sound to return helps determine the distance to an object, much like how bats use echolocation. Sonar has been crucial for underwater exploration, allowing humans to map the ocean floor, locate shipwrecks, and track the movements of marine life. Even though we encounter sound constantly, the science behind how it travels is still full of wonder. It is a force of nature that transcends distance and time, carrying with it information, communication, and emotion. Whether it's the simplest clap of hands or the complex orchestration of a symphony, sound enriches our lives and connects us to the world in ways that are both seen and unseen. Understanding how sound travels deepens our appreciation of the vibrations that surround us, from the most everyday noises to the most profound and beautiful sounds in nature.